material that we've never been quizzed on yet. I can't tell. It's going to be a final exam that covers all topics. So be ready for everything, okay? On the recap here, I was thinking, Angia, where's Gia? I thought about you after class. You asked a question during class, and we're going to take a look at that again. And you're going to remind me what it was. I think I had a -2 plus something. I asked you guys to write some terms out. And for some reason, the professor, where did that 2 come from? Something. And we're going to look at that again. Okay, guys, let me get this recap out of the way first. And that is this. Oh, in fact, it might be that problem. Gia, it might be the same problem. Okay, giving this, guys. A subscript 1 has a value of -2. Might be the same one. And then they also give me this to translate A subscript n is equal to n plus A subscript n minus 1. Gee, I think that's a problem. I think that was the one we were discussing yesterday. Now, guys, if they give it like this, and not just one term after another term after another term, they call this a recursive formula. In case you see that word in math. Recursive, they're going to set up where they give you the value for one of the terms. Here's the one of the terms. They could give you the value for a couple of the terms. In this case, they give you the value of the first term. Now they're asking me, please write some more terms out following that formula. So they use the word recursive. Gia, here we go. I think it is a problem. Let's find or write. Let's write the first. Let's try 4 terms of this sequence based on what they gave me. Well, since they gave me -2, then no doubt that's my first term. And since I'm asking for 4, I'm missing 3 here. They gave me the first one. Now, can I translate that little formula they gave me, that recursive formula? Can I translate that correctly and write now the second term? I've got to be careful. If I'm looking for the second term, guys, here goes. A subscript 2, we're going to replace an n by 2 here, is 2 plus A subscript 2 minus 1 if I apply it to this formula. Everyone agree? That's where the 2 came from. And if I finish this up, this is A subscript 2, the value of the second term, is 2 plus A subscript 1. And thank goodness they gave me A subscript 1, which is what? 2 plus what? -2? And please remind me yesterday, did we get a 0 there? Okay. Gee, see what's happening here on this one? When I try to translate it? Okay, A subscript 3 is coming up next, third term, written like this. If I apply this formula, recursive formula they call it, to this, replace n by 3, I have 3 plus A subscript 3 subtract 1, or 3 plus A subscript 2. And we just discovered A subscript 2 was 0. So this becomes 3 plus 0. Therefore, the value of the third term in that sequence is 3. If I recall correctly, I think that's what we got yesterday. Is that true? And the last term that we wish to have here, A subscript 4, if I use this formula, replace n by 4, we've got 4 plus A subscript 4 minus 1. We've got 4 plus A subscript 3. And A subscript 3 we just discovered was a 3. So this is 4 plus 3. And if I recall correctly, I think we did get a 7. You guys agree? So, you'll have one probably like this, somewhat like this on the final exam. The president asks you, can you translate what's given to you and write a few of the terms? And we have the terms written out here. Gia, did this help?
Yeah, I think,
Okay. Because you were concerned, I think, about this.
I think yesterday I was confused because I thought that we were getting the -2 from the A subscript 1.
Oh, no, that's given.
Yeah, so that's,
There you go.
that's what was wrong.
That's if they use the word recursive, they're gonna give you at least one of the terms. Could be more than one to work with. Okay, you have to use a formula to find the others. Guys, anything else here? Now, is this risky? It's risky. PK is risky because if I should, for some chance here, make a mistake, and I found here in my arithmetic I did not get 3, I got 5. It's still a mistake. Then that's going to throw this one off also. That's the risk on this. Okay, so I thought about that. Now, part B of this recap, I thought about this. Those summation formulas. Now guys, you have the summation formulas listed. I'm not going to relist those for you, but I'd like to find this. We use the summation notation. I want this one to start with 1. Let's go through 24. And it looks like this. Now I want to know the grand sum there. Now this one's I want to take a look at. Now Philip, I could write out a few of the terms just to see what they look like, but I'm certainly not going to write out all 24. I didn't add them up, definitely not. So we use those formulas, but let's take time to write out maybe the first couple. All right, guys, if I replace k by 1, because you start at the base, if I replace k by 1 in this that was given to me, I get 1 squared, subtract 7, help me out here, is that -6? -6 plus 2, is that -4?
Yes.
Altogether. So the first term is -4 at k is equal to 1. Okay, let's write out another one. Now let's go up to 2. K is equal to 2. Put a 2 in here, 2 squared is 4. 4 subtract 14, I guess. What's that, -10 plus 2 is -8?
Yes.
Let me write out one more. Now let's put a 3 in there. 3 would be what? 9 subtract 21. And guys, 9 subtract 21, help me out, -12 plus 2, -10. Is it -10 altogether? And it's supposed to go all the way out to, look at this, when you put a 24 in there. You're supposed to crunch it out and put 24. 24 squared, subtract 7 times 24 plus 2, which we could, and get some large number for the last term of that summation. I'm not going to put it in there for you. You can find it. Right there, but that's what they're asking me to add up. All those numbers, including that last one. Now you know you're not going to sit there and try to add up all 24 of those terms, but they want a grand sum.
That is a formula.
There is. In fact, this will require 3 formulas.
Yes.
That's why I brought it in. Okay, guys, if I separate this, here we go. See if this screen will work out nicely. It's working. I'm going to separate first into, and see if you guys, this might be hard to see. Is that green hard to see?
So,
Can you see it? Okay, you can see it. Okay, let's go from 1 through 24 of k squared all by itself, then subtract, just doing a separation, summation from 1 through 24. Guys, that 7 can be placed out front, which I like. These k inside. And of course on the last one there, plus summation. We'll go from 1 through 24 up to. And there it is, separate. Now why did I separate like that? Because, I'm going to circle here, there is a formula for that. There's a formula for this. And of course there's a formula for this one. Now, for a reminder, can anyone tell me what the formula was for summation of k squared? Yes?
n times n plus 1 times 2n plus 1 all over 6.
Thank you. That's the most awkward one to remember, but that's the way it looks. And I'll apply that here. This one, the summation for k, that's the easier one. I think about Mr. Gauss when I see this one. That's n times n plus 1 all over 2. The next one, if you actually want a formula here, who remembers the constant? That's what it is on the end, the constant. Summation for a constant.
It was just times,
I think called what, NC?
yes.
And those were the formulas. Let's go back and apply those formulas. On the first one, guys, here goes. I'm going from 1 through 24. Oh, it's going to be awkward, but here goes. I'm supposed to replace n by 24 in that formula. So it's 24, 25, but you're adding 1. And down here, be very careful. 2 times 24, 48 plus 1. What's that, 49? All over 6, and I'll come back to that shortly. Now I got a minus here, subtract. Now I got to do the next one. Well, the next one says go from 1 through 24 with that formula, put a 24 in. So it's 24. That's like Mr. Gauss was doing, 25 all over 2. And finally on the end, I see a plus here, merely n times c, this. And of course, 24 times 2. That's the way it would look. And we all agree the formulas applied correctly. Now I got it cleaned up. June, I may need your help back there shortly, but I'm gonna clean it up the best I can. I'm gonna cancel 6 into 24 and get a 4. That's 4,900. Thank goodness that's pretty nice. Yes, not bad. Second term with that subtraction sign, I'm gonna cancel here, maybe get a 12. Is that 300? I heard 300. Okay. And then plus 48. And then all you need to do is put those numbers all together, get a grand sum. I don't know whether anyone has it already or not. Did anyone get that?
2848.
It is 2848. And there's your grand sum. Now, you know, if you saw that somewhere at USC or UCLA, and they ask you that all they should do is this, you know, you cannot just sit there and add all those 24 numbers up. They don't want that.
We're all gonna do 28, 48. The first
What
one,
now?
It's gonna be 28, 48.
Was it 2848? How much was it?
It's 4648.
4648.
Did you multiply the 7 times the 300?
Now, look at the 7 we left out here. I left out. So that should be what, 2,100?
Yeah.
Yeah, that's what it is. Now, I think it would be 2848. Check now, guys, to see if it is.
Yeah, now it's 28.
Does it now work?
Mhm.
2848. You know, the 7 had to be brought in there. Got all involved with the formulas. But again, the thing is, you know you're not gonna be able to add all those up. I guess it keeps going on, keeps going down here, you have to add up all those. You need formulas. Yes?
Are the numbers that you get like as in kids always gonna have a pattern? Like,
There is a pattern. One of my students, she's not with me today. So there, she came up after class and she said, Professor, can I use, like you were showing me Mr. Gauss did it one way and he lined them up backwards? Remember that? The way he was doing it at 7 years old? Yes, you can do that on certain ones. Now, I know what you're thinking, Gia. I know how your mind works already. Gia's thinking, when does it work? For what sequences will it work, Ramsey, that I can do that? Oh, here she comes right now. And we were talking about that. We're just talking about what you and I were talking about after class. Remember you said there's patterns there, and she came up and we were talking about it? Yes, Gia, there are patterns, but be careful. And she had the same concern, Professor, when will it work? Hang on just a second, let me just point out what we did here. And by the way, guys, this one's finished up. My goodness, 7 there, I left it out. Gia. Woo, here goes. And we'll try a short one here. I know Gauss did 1 plus 2 plus 3 through 100. Now, you're saying 2 plus 4 plus 6 plus 8 plus 10. Professor, I know this is short, but I want to point out something here. Guys, I see 6, 12, 20, I think they add up to 30, I did it quickly. Do they? Do the terms add up to 30? Yes or no? Okay, now, the question is, could I apply what Mr. Gauss did, even on this one? In other words, Gia, I think you're thinking about this. Could I now line them up like this? And do what he did, because we'll see if it is. I think that's what you're thinking. Now, if I do that, I think we'll end up with 12 plus what? 12 plus 12 plus 12 plus 12. Is that true? And in this case, 1, 2, 3, 4, 5, and divide it by 2. I think 5 times 12 is what, 60? And you've got to divide it by 2 because you actually did it twice. Is that my original 30 we thought it would be? It worked on that. Good question. That's why I love this class and bragging to you guys. Now, we'll work on this one. Do you think it'll work on this one? Can I line them up backwards and do what Mr. Gauss did on this one, or is it different? I can't do it. Can't do it. Now, woo! Share with the class what you told me yesterday, which I thought was brilliant.
You got the pattern.
Yeah, yes.
That will work if the numbers are in increments of the same number.
That, exactly, look at this. Do they differ by 2? All the way across. Did Mr. Gauss's numbers differ by 1? All the way across, do they? This right here is all mixed up here. These two differ by what, 4? That's 4 here also. Then what, 4 here? And that's where a 9 is. They don't differ, 14 minus 9, that's not a difference of 4, is it? No, thank you so much. So if you see that difference is consistent throughout the entire summation, you can use this. Absolutely. Okay. Okay, guys. So we finally got that worked out. I love that. Gia, I think that's what you were concerned about. And you weren't by yourself. But we had that conversation after class yesterday. Okay, guys, I think, let me check and see. I'm ready to move on here. Oh, no, there's one on your paper here. Letter C. Now, I want to get some really good input from this class of all classes. How about this one? I think it's on your handout. Summation. We'll start with 1. Arena, I'm thinking about you. Arena asked, Professor, can I ever start with another number besides 1? You can. But you gotta be careful. You gotta modify your answer. So since all those formulas start at 1, I'll have mine to make sure they start at 1. Because the formulas have 1 as the starting place. You're going from 1 through, look at this craziness. And inside there, I think this is the one I had on the handout. Guys, is this the one that's on the handout?
Yeah.
Okay. Another summation. What makes this one so strange? What does it say to do? Add forever. It's infinite. You keep adding, keep adding, keep adding. You say, Professor, that's crazy. There's no answer. You just keep adding. Oh my goodness. Here goes. Let's write a few of the terms out. And watch what's going to happen. I will tell you ahead of time if everything's copied down correctly, there is an answer. And I think, if I'm not mistaken, it's an answer that you saw back in elementary school. But your elementary school teacher did not show you this version here. But you saw the answer coming down in elementary school. Does anyone have a guess as to what it might be? I heard 1. Anything else? Definitely saw one back in elementary school, right? Okay, let's see what happens here. Guys, the first term, replace k by 1 right here, that exponent becomes a 0. 1/10 raised to the 0, of course, is 1. 1 times 3/10, I get 3/10. If I replace k by 2, the next value there, I get the exponent to be a 1. So I'm going to end up with 3/10 times 1/10. That's 3 over 100. That's my second term. Let's write a few out. Third term, let's put a 3 in there. I replace k by 3, this becomes an exponent of 2. 1/10 squared is what? 1 over 100? Times 3/10, what's that, 3 over 1,000? Yes or no? And they're saying, please do not stop. And you can write out more terms. I'll write out the first 3. You can write out as many as you wish. Does anyone have an idea now? Oh, I see a hand going up. Hang on. That's some thinkers in here. What do you think it is?
1/3.
What do you think it is? Approaches what now? Okay, approaches 0, and I heard approaches 1/3. Anyone else? That would be, somehow you guys are discussing this. 0.3, Joseph, with the 3 repeating. Wasn't that the decimal with the repeating decimal? Does that not represent 1/3? When they asked you back in elementary school, 1/3 is equivalent to what? 0.3 with the 3 repeats, they put a little bar across it? Yes. So I'm hearing that 1/3 maybe. Let's see why it might be 1/3. Without any knowledge of a formula. Look at this. I know and you know from elementary school, this could be written like this. That's 3/10. This is add to it 3 over 100. 3 over 100 could be written like this. In decimal form. Then add to it 3 over 1,000, which in decimal form could be written like this. And guys, we go on forever. Well, even at this point, do I end up with 0.3, 3, 3? Which might give me a hint, Joseph, that might be 0.3 where the 3 repeats. And then that would be equivalent to, for a fraction, which we prefer here, the answer is, are you kidding? 1/3. And they call this infinite. I see why infinite, because it goes on forever. That's the infinity symbol. Then they call it geometric. And guys, can someone tell me, I looked at a pattern over on the other side there with some student input. Can anyone tell me, is there a pattern here on these terms to move from one term to the next term? What are you doing to go from first term to the second term to the third term? What are you doing? Over here, I was adding 2. They differ by 2.
Yes, which is times 1.
Yeah, times how much?
1/10.
1/10. You're multiplying a term by 1/10. You multiply this by 1/10, it'll take you here. You multiply this one by 1/10, it takes you here. And they call a summation like that, a sequence like that of terms, geometric. That's a common, they call it the common ratio. But anyway, 1/3. I would have thought that. Now, by the way, I don't know whether I placed a formula on your handout. Did I place a formula that you could have used to get that answer? Or not? Or did I say anything about it? I think I said something about it. Who would like to read for me before I leave that? What did I say about this? Yes, read for me, please.
If the absolute value of r is less than 1, then the summation of k equals 1 to infinity ar to the power of k minus 1 equals a over 1 minus r.
Oh, hang on. So you're telling me, by the way, let me point out, guys, this right here is my ratio. They call it a ratio. That's the number that we're multiplying each term by to move from one term to the next. I see that up there, multiplied by 1/10 to go from one term to the next. They call that a ratio. Now, on the handout, you're telling me if I take the absolute value of that, I think, and that comes out to be, in this case, 1/10, of course, and that's what, less than 1?
Yes.
If it's less than 1, comma, there's a formula you could use to show it's 1/3. I know you have enough formulas as it is. So if you saw something like this on the test, I would give you one where you just write out a few of the terms and you can see a pattern there and get the answer. What was that formula again? Remind me.
Summation with k equals 1 and up to infinity.
All the way through infinity, okay.
AR to the power of k minus 1
Okay.
equals A over 1 minus R.
A over 1 minus R. If you'd like to use it, I'm going to just throw it out there. Now I'm going to use it here. I checked the absolute value of the ratio, absolute value of 1/10 is 1/10. The statement says if that number 1/10 is less than 1, it's going to be less than 1, then you may find this infinite summation by using this formula. Now I'm going to use the formula here, guys, right here. In this case, A, my first term was 3/10. That's the A. Over 1, subtract the ratio is 1/10. Do not let me make a mistake here, that's what, 3/10 over what is that, 9/10? Gonna do my math there. 10's canceled. We've got 3 over 9, which reduces down to, look at that, 1/3. Oh my goodness, another formula for me to remember. But I would throw that, I'm going to bring that out. Some instructors do not show this. I thought for this class, maybe you'd like to see it, maybe something nice on for an extra credit on your exam. I would think if I gave you this as the extra credit, I would think most students say, Professor, I have enough formulas in my mind. I'm going to just do what you did. From elementary school, just add them up and get a hint on what it looks like. In this case, 0.3 with a 3 repeats. 1/3. With you guys? Did I say anything else about this, or was that it?
It's just said a series that does not converge is called.
Oh, beautiful, beautiful. Now I heard the word converge. Look at this, guys. Use this word in mathematics since my students are moving on. It converges to 1/3. We accept the answer as 1/3 though, but they like to use the word it converges. Wonder why they like to use the word converges to 1/3.
So
Will it ever get there?
No.
No, because the sum goes forever. But it gets so close. Look at those threes there. 0.333333333 keeps going. It gets so close that they say it converges to 1/3. I probably used another word there also. Yes, go ahead.
Would that then be like what we were doing before with the limits, where it's like, if we find like, the limit of k as it approaches infinity,
Yes.
it should converge?
Yes,
Okay.
like k is approaching infinity, absolutely. Now, did I use another word there to close this down? Did I use the word diverges? I think did I throw that word in? Okay, it diverges, this one did not. Here's the word. It's a little vocabulary. It diverges if this does not happen. In other words, it does not come out to be a nice 0.3 with the 3 repeats. It starts getting larger and larger and larger. You keep adding forever, and it just keeps getting larger and larger. It does not approach something. Mine approached 1/3. Okay, and they say therefore it diverges. So converges, diverges. Guys, any questions there? I don't think I had anything else there on your handout about this. I don't think. Try and get this cleared up. Guys, do it? No, I think that's it. That handout's finished. Does that make sense the way we approach this? So please, for your extra credit, if you see one on the final exam, I told you there's about 10 to 12 extra credit points. And you see one like this, you say, oh, Professor, you've gone crazy. You could, if you want another formula, here it is. Or you could write them out and see what the pattern is to get the answer. Okay, guys, I think I'd like to bring that in there. Now all that's done. I think it's all done. So we did some sequences, we've done the summations with the help of the summation formulas. Oh my goodness, I think all that particular section now is done. Okay, now, I'm gonna erase this. carefully what I intend to do next. This is 11.4 coming up. I'm gonna make it short. Call this, I guess, part 3. Okay. Here it is. Math induction. Step back and look at it. Math induction. June, Mr. Park, in all your math, has the professor ever, have they ever approached a proof by using what they call math induction? I see Jude says yes. Mr. Park, no?
I never heard that.
You never, well, you heard it from me in your math too.
I might forgot it. Yeah.
I'm not talking. But June says in one of her classes, probably, what, one of the calc classes maybe, or not? Or was it math 2?
It's math 13 and 10.
Oh, is it?
Yeah.
So there's higher classes in. They do something called math induction. Now, here's what it is. That's why I'm going to just keep it as simple as I can here for math 2. It's this. Oh no. They're asking you now not to solve and get an answer. They're asking you to prove. They may give the answer to you and ask you to prove it. And we're going to do it by something called induction here. Now I brought one in and I got a nice, if I can find everything here, oh gee, did I ever. Hang on. Sure everything's here. Mr. Park, when I get ready to pass these out, I'll make sure you do help me pass these out, because you said your memory was leaving you?
Oh, sorry.
I think when you see this, you'll remember. We did this in math too, so we'll get this in short. First though, I'm gonna point out this, one side to the other, all this done. Yes, here goes. Show the given statement is true for all positive integers. So we'll give you a statement. We're supposed to show, prove, that that given statement is true for all positive integers. Now, if you ever watch something, watch carefully on this. It's a little bit different for a proof here. I brought one in, and what I see on the handout, another one here. This statement looks like this. It's a summation. There's no statement. We're still doing a summation. That's like a formula. They're saying prove it. Guys, first just read it. Sometimes you'll have a statement in math that the professor, I don't even know how to read this. That makes no sense to me. Can anyone tell me, because if I stare at it right now, I actually see two formulas. I see something on the left, I see something on the right. Can anyone tell me what the 2n on the end there on the left tells me? If everything copied down correctly. Anyone have an idea? Right in that with 2n on the left, what does that 2n represent? That needs some help. There we go.
The end number.
Okay, tell me more.
The end of the sequence.
Oh yeah, that could represent the end of the sequence, or series, they call it series now, for a summation. That was something else. Just quick quickly, what do you think two n on the end tells me? Yes?
That a subscript n equals 2n.
Okay, I could, a subscript n is equal to two n, love that, the last term, like you mentioned also, easier than that. What on earth is that two n on the left telling me?
Wrong.
It's just staring at you. June.
That every number in this sequence is multiplied by 2 and 3,
No. I followed your logic. A little bit easier. You almost have it.
Summation.
No.
that goes on forever.
No, I'm staring at you, you don't know what you're looking at. That's the way I was in grad school with my math sometimes. Look at it, what on earth is this? But it is. I should replace n by 1. Suppose you didn't see all this. You saw the formula on the end. You didn't see all this. And you replace n by 1. That gives me the first term. If I replace n by 2, it gives me the second term. N by 3, I get the third term. So that's like, it's a formula, and in this case, if I should replace, if I wish, on the left, n by 50, that tells me my 50th term on the left, if I should write all the way out to it, has a value of 100. That's what it tells me. The truth? Now, the harder question is, what on earth does this thing tell me on the other side? That's a formula also. You'll be shocked what it tells you. I hope I have everything copied out correctly. And before I leave it again, if on the exam, I ask you first before you start the proof here, Arena, I'd say on the left, Arena, real quickly tell me the value of the 75th term real quickly. Guarantee, if you should write all the way out to the 75th term on the left, what is its value? You quickly do what to find it? I want you to think the value of the 75th term. No summations. Nothing, you're making it hard. What's the value of the 75th term on the left? You're gonna put a 75 right there. And what's 2 times 75? 150. Guaranteed. You should write out the first 75 terms. The 75th term on the left will have the value of 150. That's all it takes. That's all it's telling me on the left. Ooh, Philip. What? This is the harder part. What's this telling me? N times n plus 1.
We just writing the summation
Oh, beautiful, we will. We're going to rewrite this using the summation symbol shortly. You know what? Hang on. I think Sue's already thinking. He said, Professor, I know you're going to do it eventually on that left-hand side. Are you telling me, Wayne, tell me, are you saying, Professor, you could rewrite that as maybe start with what, k or n, n's equal to 1, through what? Or we want k here maybe? K might be better. Through n of 2k? Is that what that on the left-hand side really represents? If I replace k by 1, I get 2. Replace k by 2, I get 4. That's a summation. K by 3, I get 6. And finally, when I reach down here, replace by n, do I get the 2n? Is that a good way to represent what's going on? Are you thinking about that? I love it. Love it, love it, love it. Hang on. Wow. I'm not thinking that. I love it. But, let's get back. What on earth is that telling me? June.
It's the formula for the sum, so it's telling you that no matter what the n term is n, the sum of all of those terms will be the number, will fit into that equation.
Would be n times n plus 1. Okay, guys, let's see what her reasoning is here. If you were asked now, watch carefully. She's saying, Professor, this on the other side is telling you something about sum. It's not telling you a particular term like I asked Arena for the 75th term, which had a value of 150. It's not that, that's on the left. This tells you the sum. Now watch what happens here. If I go back to the left and sum up the first 2 terms, that's 6. Is that true, guys? Now how many terms was I working with here? 2. So if I go over here to the other side and put n to be a 2, in that they gave me, I end up with 2 times 3, I get 6. Let me add up the first 2, 4, 6, I guess the next one will be an 8. Let's add up the 2, 4, 6, 8, help me guys. 6, 12, is it 20? If you add the first 4, I think it's 20. Okay, the first 4 add up to 20. That's when I put a 4 there, that's right. 4 plus 1, that's 4 times 5, 20. June, I think that's exactly what you were thinking of. That's exactly what you were thinking of there. Now, I'm gonna go check this one, let's find real quickly. Here we go. Let me throw it in there. Suppose I want to know what the sum of the first 50 terms on the left-hand side would be. You're staring at the first 3. I want all 50, or up through 50. I want to know what the sum would be for the first 50 terms. I said, Professor, go to the formula on the right. I think that's that, which is 50 times what? 51? Guys, what is that? 50 times 51, help me out. 2550? 2550? And that's what that means. Now, Wayne, wow, we need to be, other students need to hear what you guys are doing in here. Wayne says Professor, you can write the left-hand side using a summation. This right here actually says this. Now, suppose I apply now a formula from yesterday. Let's make something connect here. Suppose now, stick Wayne, I'm gonna move that 2 out front. Look at this. DK. You're going from 1 through n. Guys, I need now, help me out, got the 2 out front. Now, what's the summation for k? There's only 3 formulas. Remember what it was? Love it, love it, love it. I go further, 2 still up front, I will not forget that this time. And in this case, guys, I know it says go through n. Let's try something here. The last one, we went through 50, didn't we? We went through 50. Let me change this to a 50. Let's see what happens. You guys got, what is it here with the help of the formula? Oh, by the way, that's nice that it works out like that. Would these 2's actually cancel? Please tell me, even right now, would these 2 cancel? Does that take me back to what they gave me here originally? Is that a way to sort of justify? Yeah, I can use one of the summation formulas from yesterday and actually justify. In fact, I don't need to show 50. I just want to actually show it works. I keep that. These cancel, and you're going to end up with exactly n times n plus 1. Oh, Wayne, look what you did for the class. There it is. Make sense? All this just connects. Absolutely. Now, though, here's the problem here. This is where we're going to start the work here. They want us to show that statement's always true. That's always true. Marina, math can do strange things. I've seen some of these, and I think the textbook may point out a couple of these, where the statement they give you, you can say 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14, and you stop there and you add them up, and then come over here and put the n number in there and see if they check, like I was doing 50. And then all of a sudden something happens after that and it will not work. Something happens to the summation, and for some reason it works up to a certain point, makes all kinds of sense, and all of a sudden it does not. So they want us to try to show the best we can that this always works. Now, guys, here's the way it goes. Here's the proof. This is induction. Step 1, and you must write these. I write out what I'm writing out here. The statement must be written. First, you show statement is true at or for n's equal 1. please make sure the statement is true at the very beginning. If it's not, you say you have a false statement, Professor. That statement is false. So step one says, please show initially it's true. Now, Phil, what does that mean that I need to do? I need to go back to my statement. Here we go. Here's the statement. My first term on the left is 2. That's what we want. First term. Left, 2. And over on the right, you're going to replace these ends by 1. The first term. 1 times 1 plus 1, which is 1 times 2. Please tell me, does that agree? So if I just pull out the first term, and we go to the other side and replace k by, in this case, 1, it looks like the statement is true at the beginning. That's all you have to show me. That's true at the beginning. That this matches up with this on the other side. Two sides match up, in other words. Guys okay so far? So it's true at 1. Number 2 here. Now, I gotta describe something. Joseph has already plugged in 1. He got the easy one. He says, Professor, 1 tells me that 2 is equal to 2. Thank you, Joseph. Then I go to June. I said, June, they're saying it should always work. I said, June, policy names choose. Where am I? Right here. So I said, June, please replace it by 2. June said, Professor, no problem. I'll show you it's true at 2. So she'll go here and say, I'm going to add it to the first 2. Get a 6. And down here, put a 2 in, which I think I did. You get a 6. On the other side, they match up. Professor, no problem. Wayne, I come to you. I said, Wayne, would you please put in a 3? We're supposed to test all of them. Put a 3 in. He says, no problem, Professor. And at the first 3, I think it's 12. And if you go down here and put a 3 in, 3 times 4, they match up. The statement is true. Philip? 2, 1, 2, 3. You want to put a 4 in there for me? I say, no problem, Professor. 2 plus 4 plus 6 plus 8. And guys, that much right there would be what, 20? I think, was it? First 4 would add to 20. Now you're going to put a 4 in down here. I'll get you 4 times 5. You get 20 again. Philip smiles, I smile, the class smiles. We're good. The arena, you're going to put in 6. Zoe, you're going to put in 7. Over here, you're going to put in 8. Selena, 9. Selena, 10. All the way around till I reach my last student there. In fact, I'll probably go all the way down to Mr. Park. And by the time I get to Mr. Park, my goodness, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. He's number 19. Oh, he gets one of the worst ones. He's got to show me, he's got to add the first 19 terms. Good luck, Mr. Park. And then replace over here, ends by 19. And show me the two sides match up again. And then Mr. Park, I know how he is, he could do it. He said, it may take me a little time, Professor, but I'll do it for you. Now, am I satisfied it's always true? No, I'm going to open that door and see if there's someone out there just walking around, not doing anything. I'll ask them to come in. So I need some help. Would you please now replace this by 20? And show me it's true at 20. Now, am I going to say, yeah, it's always true? No, I've got to find another student, show me it's true at 21. PK, it goes on forever. Right? You think driving home in traffic on the freeway tonight, if the traffic's slow at night and that's the person next to me, I need a favor, could you replace, I'm doing some math at my math class. We stopped at 50. Could you add these up? And you go, crazy, crazy. Crazy. It keeps on going. So what must we do? We have to assume. Ooh, I don't like that word, but we have to assume it's true up to a certain point. Let's say we did go all the way through and Mr. Park had 19. And he was patient enough to go 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16. The first 19 terms. He was patient enough and he got a grand total. And then he goes over here and puts a 19 in. He said, oh, Professor, the two sides match up. So we just assume it works up to a certain point. I can't just call people in and company out here. It goes forever. So what we do is, step 2 is, we're going to assume the statement is true. Look at this. At n is equal to, your textbook calls it a k. My k in this case would be 19. We're assuming it's true up to that point. Okay, guys? That's the assumption. My students in this class have shown it's true through 19. That's my k. Now, how's the statement look at k? Let's go back. It says 2 plus 4 plus 6, so forth and so on, plus 2k, and replace the n by k on the other side. That's what the statement looks like at k. And we're assuming that's true. I know this proof of induction is a little strange way to prove something. So far, so good. So that shows it's true up through k. Now, last statement. Now you gotta show, to close this down, that the statement is true.
K plus 1.
Look at that. Hang on. When Mr. Park finishes up, says, Professor, that statement's true at 19. I was patient enough to add all 19 terms on the left, and I put a 19 in for the n on the right, and they match up. And of course it says, sure it's true for all. Then I need a student outside to come and show it's true at 20. Then if that student says, oh, that's a long problem there, but it works. I say, well, I'm not satisfied now, it does work at 21. What would be a good representation to show after k, I need to show what? K plus 1. You gotta show it one more, one more, one more. It's true at k plus 1. And when I do this part, that's the last part of the statement. We gotta show it. It's true. Guys, does that k plus 1 make sense? Mr. Parks, number 19, we're not quite satisfied because then I'm looking for the next student to show it's true at 20. Then the next student shows it's true at 21, and 22. It continues forever. Okay, show a statement is true at n is equal to k plus 1. First, let me see what this statement looks like at k plus 1. Let's go back. 2 plus 4 plus 6 plus that plus, now look what I'm going to do here. 2k. We get that from the step 2. It's true up to that point. Now I'm going one more. Let's put it in a different color here. Make some sense of this. Try orange. Plus, I hope you guys can see this. Can anyone tell me on the left-hand side, what would it look like, the last term now look like at k plus 1? We've already shown it's true, all this right here. This is step 2. Now you're saying, no, Professor, don't stop there, go one more. Can anyone tell me what on the left-hand side the term now on the end would look like at k plus 1? Thank you. 2 times k plus 1, 2k plus 2. And we're trying to show that that's equal to, look at this, it looks a little strange here. That's equal to, now can you tell me what the other side looks like at k plus 1? When you replace the n's by k plus 1, what might you get over there? Help me out, guys, someone.
K plus 1.
K plus 1 for sure, and?
Times K plus 2.
Love it. Love it. I notice those colors. Well, those colors for a reason. Does everyone agree with k plus 1 and k plus 2? If you go over here and put a k plus 1 here, a k plus 1 there, k plus 1 plus 1 makes that k plus 2. Now, if you show those two sides are equal, we're done. I'll show you how easy it's going to be. Show. Look at this. A little separation. This much in the purple. That's why I use different colors here. That much has already been established to be equal to what? From step 2. You draw an arrow. What did step 2 say all that I just blocked off is equal to? Look back at step 2. What is all this right here equivalent to, equal to, by step 2? K times k plus 1. Right here it is. So all this is equal to this.
So we need to always keep this one.
Yes, you're going to bring that step 2 always down to your work. I still have though down here this. And guys, we'll go ahead and, well, I'll leave it to k plus one, let's multiply it out. Let me step and look at it. Now, would you guys like to now, by the way, now you guys show the two sides are identical. We're close. We got this from step 2. We got this in the orange. I gotta put these together some way and get this. If I can, we're finished. Does anyone see any way to do it?
Take out k plus one.
Oh, they got k plus 1 as a common factor, look at that. If you take out k plus 1 on the left as a common factor, you're left with this for the first term. And what are you left with when you take k plus 1 out of the second term? A 2. Do they now match up? Are the two sides identical? Not here, thank you. Now, if you didn't see that as a common factor, which I love though, some students may say, Professor, I saw it more like this on the end. Why not just multiply that out and call it k squared plus k, distributive property. And down here, 2k plus 2, like that, and make it a nice little quadratic. Another approach you could take here. And therefore, guys, this down here, if you want to use the distributive property like I did there, is k squared plus 3k plus 2, which I think factors into, check and see if I'm right, does it factor into that? Which is what we want. That's another way to approach it. Wow. Wow, wow, wow. Gee. Now, I'm happy. The textbook, I think, actually showed that all this is true. The big part's right here, show this statement's true down here. Then everyone's happy, and they usually say at the end here, they write a concluding statement. Yes, this statement is true for all integers. Not just 19, not just 20, all integers. That makes sense? I noticed the first, probably